Okay. So congratulations, all those who have reached this point here and haven't given up, because this was definitely not, as we said from the start, it's not going to be easy. So congratulations, you've gone through this. So let's review, contemplate what we did, and also think what's next, in case you want to do more than just what we did here. So we started with a statement of computational integrity. So a prover comes along and says, hey, you know, the element number 1024 in the Fibonacci sequence is this value. In this particular kind of Fibonacci square sequence, modular Fibonacci square system is some value. And that's the statement to be proved. And what we want to do is get a proof that is exponentially faster, that verifying it would be exponentially faster than sort of doing the naive replay and sort of going through the 1023 steps, okay? And the way we did this is we required the prover to do a lot more work than just doing the computation. In particular, the heaviest part was to sort of take the computation trace, which is generating it takes pretty much the same time as running the computation, but then applying this heavyweight encoding step that takes this information and adds a whole lot of redundancy to it through this error correcting code, and that's the execution trace. Then we requested the prover to take that information and do another heavy weight operation, which is apply the composition polynomials, those rational functions, to it, with the understanding that if the prover is honest, then something good should emerge, which is that at the other side of this transformation, what the prover gets is a bunch of low-degree polynomials. And then we basically combine those, and assuming these were low-degree polynomials, we asked the prover to do yet more work and generate commitments for the Fry protocol that went and shrank in size. And then we forced the prover to sort of answer a whole bunch of queries to these commitments that he previously made. And because, again, working our way back, because the queries were sort of answered correctly, we learned from that the commitments were good and proved that the composition polynomial was a God-honest low-degree polynomial, which then makes us convinced that the computation trace is valid and satisfies all the constraints of the computation, which then implies that the statement is correct and the 1024 element in the Fibonacci square sequence is that which was said. Okay, so that's what we did here. So some food for thought. If you look at the proof as it ends up, most of the sort of the bits are associated with Merkle authentication paths, and only very little information comes from sort of checking the queries. So moreover, if you fix the sort of blow-up factor for the polynomials, what is known as the rate of the code, and you fix the security parameter, like the amount of error you're willing to tolerate, then essentially the number of invocations of the query protocol is constant. It depends only on those two parameters. So what does change as you increase the amount of computation is larger trace means that you sort of have larger authentication paths and more layers of Fry, and you get a log squared blow-up factor as you increase. One log comes from more levels of Fry, and another log comes from the fact that each one of these is sort of longer. And this also means that the amount of verification work scales like log squared. But, so it does grow, but it grows very slowly, right? It grows exponentially slower than the amount of computation, and which means that the verifier is what we call succinct. The prover needs to evaluate the composition polynomial on all the evaluation domain, and the proving time grows quasi-linearly, or n log n, with the amount of computation. Not in the code that you guys wrote, because it was optimized for didactic efficiency, but there are efficient algorithms based on FFTs that will make the provers work quasi-linear. So what we get in the end is a system in which the verifier is succinct, or exponentially, logarithmically small in the amount of computation, and the prover is quasi-linear. And we say that systems that have both of these properties, where the prover is very efficient and the verifier is very efficient, we call them scalable, because they allow you to deal pretty nicely with computations that scale in size. So what we haven't done, and you're welcome to do, and if you do it, then please also share the code. Others would like it as well. So first of all, to write a verifier, we only wrote the prover. Another thing you could do is, instead of using this very specific recurrence rule that is the Fibonacci square sequence, you could think of some other recurrence rule that maybe takes 5 elements in the trace and applies a degree 4 polynomial to them, mixing them in some weird way, right? And if you ask yourself, why would you want to do such a thing? So a lot of the contenders for Stark-friendly hash functions are actually pretty close to this description. For instance, things like MIMSI or gMIMSI and Hades, Poseidon and Rescue would use a recurrence rule that looks pretty similar to what you did, but slightly different. Another thing you could do is just take and prove a completely different computational statement, one that is more elaborate. Maybe it has a conditional statement, right? Maybe it has more than one register, and it sort of combines them in various intricate ways. And the last thing you could do is optimize the performance. As I said, the proving time here will grow polynomially, at least like n squared, where n is the number of steps, because the interpolation and evaluation that we used here are not necessarily most performant. You can optimize it further. All the material, if you want to do these things or learn more, so all the material for this thing is going to be online. If you want to if you want to understand the math better, you can read the blog posts. And if you want to understand them even better, then those blog posts actually refer to papers that you can go on to read. If you want to know what we're up to, so please follow us at Starkware Ltd. Another thing, so at the SBC, we'll be presenting a Stark-based VDF and some other applications to time locks and things that you can use Starks with. And by the way, the prover that you wrote, if it is optimized enough, could work very well with those with the system that we'll be presenting. So you can actually boost it up and transform it into something that could work with a VDF on the main chain. So I want to thank you all, and I also want to thank our terrific team. So we have here Shiri and Uri and Alessandro, but most of all I want to thank Kinneret and Itai, who worked very hard on this thing, and also unfortunately 2 others that were supposed to be here but couldn't be for this are Arij and Shir Peled that are also behind this thing. I'm basically just reading out the slides that this magnificent team has done. And I just want to end by requesting, there's a very short 5-question, 1-minute survey that we'd like to ask you to fill out if you're willing. This will help us sort of improve the next time. So if it's fine with you, you just need to sort of type in this thing and just reply to this. And thank you all very much.